Let's talk about hemoglobin and some hemoglobin pathologies. We'll start by just going through the dissociation curve, which you guys should be relatively familiar with. Talk about carbon monoxide poisoning, methemoglobinemia, which is really just where the iron gets oxidized to a 2 plus to a 3 plus state, and then cyanide poisoning. So everybody should be super crazy familiar with red blood cells. Red blood cells carry hemoglobin. Hemoglobin carries oxygen. 4 oxygens per hemoglobin. There's cooperativity, where the binding at one subunit increases the likelihood that the next subunit will bind oxygen. Each of these subunits gets their own heme molecule, which has iron at the center. Hemoglobin dissociation curve. So here we have the arterial oxygen pressure, PaO2. And note that, so this is showing the oxygen dissolved in the plasma. Notice what a ridiculously, compared to the total amount of oxygen, majority of it is oxygen that's bound to the hemoglobin. So this is what's actually contributing to the pressure. And yet most of the oxygen is carried by the hemoglobin. So if we went from, let's say, like 30 to 60, that's an increase in 30 in terms of the PaO2. That is a tremendous increase in the amount of total oxygen content from, let's say here to like there. That's a ridiculously large increase. What if I went from like 100 to 130? That's almost no increase in the total oxygen, because we're pretty much, it's not going to, the solubility is all spent up. All of the hemoglobins are bound. That's mainly what pushes oxygen into the blood. And additionally, for the tissues at rest, we're really only going from, if we're starting at like 95, 98, 100% oxygenated hemoglobin, we're going to, I don't know, it's going to vary, but maybe we're going to lose about 20 to 40% of our oxygen in a normal cycle as we go from the lungs to the tissues and back to the lungs again. So we have this huge amount of reserves when hemoglobin travels through the blood, which is going to be important for a rainy day, right? If we're running from a bear or whatever. Now, this curve can be right-shifted and downshifted. There's a tense version of hemoglobin that is likely to dislodge oxygen, and a relaxed version which is likely to bind or hold on to oxygen. So right shifting is going to favor the tense, left is going to favor the relaxed. So in other words, this is going to release oxygen, this is going to hold on to oxygen more tightly. So fetal hemoglobin binds more tightly. Carboxy hemoglobin, when CO binds, makes the subunits that don't have the carbon monoxide, those bind to O2 more tightly. Methemoglobinemia is complicated. The particular heme subunit, the iron that is oxidized for the 2 plus 3 plus state, that is a lower affinity for oxygen. But the other subunits, right, if only one subunit is oxidized, then the other 3 will actually have an increased affinity. So depends how many subunits are affected, et cetera, et cetera, et cetera. But we're going to overall say that there's an increase in affinity. 2,3 BPG or DPG is just, if you go up in altitude, you create more of this. This binds to, this is some negative thing that binds to positive amino acids within the hemoglobin, stabilizes the tense conformation. And now these 3 really go together. Now, what do high CO2, low pH, and high temperature have in common? Exercise. If you're exercising, you're exerting a lot of CO2. There's a high ventilation rate, a high cardiac output. Your muscles are consuming a lot of oxygen, generating a lot of CO2. So high CO2, that makes sense. You're going to be breathing more of that out, more of that's in your blood. CO2 combines carbonic anhydrase with oxygen and forms carbonic acid, which is an acid. That's going to lower the pH. Additionally, some of your muscles are going to switch over to anaerobic respirations. You have a lot of lactic acid. Lactic acid, again, that's an acid. That is going to lower pH too. And look, sweaty, high temperature. All 3 of these things are going to collaborate. We evolved hemoglobins that responded to these 3 things to become, to enter into the tense state, to relax the oxygen, which makes sense because if I'm exercising, I don't want to hold on to my oxygen. I don't, that 20 to 40% that we normally, switch, cycle in, we want to go above and beyond that. Now it's the rainy day, we want to offload more oxygen, so we need the tense state. So that should check out. All right. The Bohr effect is really just that CO2 knocks off oxygen. And the Haldane effect is the opposite. Oxygen knocks off CO2. Now, specifically, CO2 is converted to carbonic acid, which dissociates this hydrogen, becomes bicarbonate. Bicarbonate travels in blood. That's like 70% of the CO2. But this binds onto the hemoglobin, stabilizes the tense conformation, and that is going to make the oxygen more likely to leave. And pretty much the opposite for when oxygen comes off, comes into the picture. It's going to bind, stabilizes the relax, which kicks off the hydrogen. Hydrogen combines with bicarbonate. Bicarbonate and the carbonic anhydrous reaction makes CO2, and then CO2 can be breathed out. This is in the lungs. This is in the tissue. When you go up in altitude, it's 21% of the atmospheric pressure is oxygen. That doesn't change if you go up in the air. It's just the total amount. So we might have 760 down here, and we might have like 400 up here, but it's still 21% regardless of where you are. And this is sometimes called a fraction of inspired oxygen, that 21%. So if you go to a high altitude, let's actually say that this is normal. So here's normal. Maybe we get like 100% of our hemoglobin saturated. And then when we go to the tissues, maybe this is going to be, let's use their numbers. This is going to be 62%, right? So we have offloaded 38% of our oxygen. And you might say, wait a second, what about the oxygen that was in the plasma? Remember, that is such a small part of the picture that we're going to, for the most part, disregard it. So we're really just looking at, we can more or less treat it as negligible. The amount of oxygen is reflected by the amount bound to hemoglobin. So we lose 62% of our oxygen normally. So what happens at high altitudes? Well, at high altitudes, you're going to have hypoxia, meaning you can't get enough oxygen in the blood because there's, instead of, there's just not enough getting in your lungs because there's so little oxygen, right? There's not a lot of atmospheric pressure. So maybe we're going to get occupied at about, I don't know, maybe this is, oh gosh, now I got to do math. This is 30%, so, and I'm going to 62%, so I guess this is going to be 92%. So instead of getting 100% oxygenation, now we're just going to get 92% saturated. But when we go to the lungs, though, actually that should be right here. So 92% is right there. That's how much we pick up when we're on Mount Everest. But okay, so the important thing is that the tissue PO2 doesn't really change. It's only the arterial oxygen that changes, the amount coming into the lungs. The amount of the tissues is the same. So we shifted from here to here for lungs, but the tissue stays constant. So now if we're at 92% that we pick up, we're still going to offload. And gosh, now my numbers are all crazy off. Sorry. All right. The last thing, let's say that this is 80%. No, that's actually fine. That's totally fine. So 92%, and now we're at 62%. So now we're only losing 30% of our oxygen. We need to deliver 38%. We're only delivering 30%. That's not enough to feed our tissues. We now have ischemia. Or maybe not ischemia, but we're some sort of hypoxemia and hypoxia. To fix this, the 2,3-BPG is going to shift everything to the right. So yeah, maybe we pick up a tiny bit less oxygen now that we do this right shift. The 92%, by the way, should have been over here. This is what I should have said, 92% to 62%. And now that I do a right shift, now I'm making up these numbers on a fly, which is probably a bad idea. So now we're picking up, let's say that the number is 89%. Let's do 89%. So now we pick up 89%, right? Because we did a right shift. So we're picking up a little bit less oxygen. Instead of 92%, 89%. This might seem counterintuitive. Wait a second. The whole idea is you want more oxygen. Now we have a tense hemoglobin that can't pick up oxygen, getting 89 instead of 92. Yeah, but the idea is, yes, it's picking up a little tiny amount, 3% difference in the lungs, but the effect on the tissues is so much more pronounced. Instead of going to 62%, now it's going to 52%, right? So now this 89% to 52%, this is going to be a 37% delivery. So the amount delivered is what I care about. So that is why we're going to favor the tense conformation of high altitudes with 2,3-BPG and whatnot. Sorry, I kind of screwed that up, so feel free to play back. I screwed it up, but then I landed the plane. So what I said at the end is correct. Hemoglobin concentration, we got all these different terms. So hemoglobin levels really just reflects the amount of red blood cells, more or less, right? The more hemoglobin, the more red blood cells, assuming that you don't have some sort of like microcytic anemia where you're really crap at producing functional hemoglobin or hemoglobin period, right? You have normal levels of iron and things like that. No thalassemias, etc. Hemoglobin saturation more or less reflects is indirect measurement of how much oxygen you have in your body. If you have low hemoglobin saturation, you might have low oxygen. Alternatively, it might mean you have some sort of hemoglobin poison thing going on, or perhaps you have a just defective hemoglobin by some other metric. But so you could get two different things from the hemoglobin saturation. Dissolved O2 is really just saying how, what's our ventilation rate, how much oxygen are we bringing into the blood, and then, into the lungs, and then how well is that diffusing, doing the gas exchange at the alveoli with the pulmonary capillaries. And the total O2 content is going to be some sort of reflection of both of these combined. So carbon monoxide poisoning. So normal combustion, where we have excess oxygen, notice this is a 2-to-1 ratio, makes CO2, which is fine. But if you don't have enough oxygen, you do what's called incomplete combustion. Now, this is a 4-to-5 ratio, right? We don't have as much oxygen compared to the amount of hydrocarbons that we used to have. Now you start to produce carbon monoxide. Carbon monoxide has these 3 resonance forms. Which one is the best? Well, this is the only one with a full octet on the carbon. So despite the fact that we don't want our carbon to have a negative and oxygen to have a positive, this is the best one. This is the one that you will see reflected because it is the full octet, the best resonance form. When will we have incomplete combustion, thereby producing this? You will have it if you have a car in the garage, the exhaust is running, incomplete combustion, and the garage is pulled down, so like house of cards, and it's going to fill and you're going to suffocate. Fires, just in general, are going to produce carbon monoxide. Heaters for your house might also produce carbon monoxide. Note that carbon monoxide is, and this negative is 200 times. Think of O2, right? O2 is, maybe there's a little bit of like van der Waals forces, instantaneous dipole-induced dipole stuff going on, but for the most part, this is a relatively nonpolar molecule. So oxygen, the affinity it has for a positive iron is going to be a little bit less than this C- has for oxygen, because, minuses and positives are attracted, so it should make sense that this affinity is so much higher. Luckily, though, carbon monoxide is pretty crap at diffusing through the alveoli. It's diffusion limited, meaning it doesn't diffuse as fully as it would want. Like the blood's flowing through quickly to the pulmonary capillaries, that there's not an equilibration that is achieved with carbon monoxide. You do achieve it if you have healthy lungs with oxygen and CO2. So those are called perfusion limited, where the amount of gas getting in and out of the lungs is only limited by the amount of blood flow, not the amount of gas in our alveoli, but that is different with carbon monoxide, luckily. Carbon monoxide competitively binds with oxygen. We just saw that it's negative. It binds really well with iron, and if it binds, oxygen cannot. So less oxygen will be bound. That is why we're seeing all of these shifts. So if I have 0, that's what this is specifically showing oxygen hemoglobin. The more carbon monoxide, the lower this is going to go down, because carbon monoxide is outcompeting our hemoglobin. It also, though, we said that it has a left shift or an upshift on the hemoglobin dissociation curve, so it also inhibits the offloading of oxygen. So the other subunits that don't have the carbon monoxide hold onto the oxygen more tightly. This is called carboxyhemoglobin, or mono-oxyhemoglobin, not to be confused with carbanohemoglobin, which is where CO2 binds to the hemoglobin. Note as well that the blood will still look like red-ish, maybe a little bit overly red, which we'll get to, but the blood still looks normal, and our pulse ox might actually pick up a normal value, because while this is showing oxygen saturation, this is just picking up hemoglobin saturation, period. It can't differentiate between an oxygen and a carbon monoxide molecule. So this could be misleading. I could have severe carbon monoxide poisoning and have this value still be high. So signs and symptoms: cherry red skin. So I don't know if you necessarily get hemoglobin to be more red when it's bound to carbon monoxide. Quite possible, but you have a hard time offloading this carbon monoxide. So your venous, like normally we dump a lot of our oxygen off in the tissue capillaries, and then in the venous system, blood is blue because it's not filled with oxygen, and so it's blue, not red. But if carbon monoxide is there, it'll still look red. So this high venous amount of hemoglobin saturation makes people's skin look red. When you die, you have even more blood pool in your veins because your heart's not pumping anymore. So in the post-mortem, it's going to become even more pronounced, this red thing. But you can maybe see like cherry red lips or something on somebody who has carbon monoxide poisoning. The globus pallidus in the brain is going to have these little lesions. People are going to be dizzy. They're going to get headaches. And of course, they might just pass out or have a seizure or die. Carbon monoxide also inhibits complex 4 of the electron transport chain. So the treatment is supplemental oxygen. Why? Well, this is normal hemoglobin bound to 4 oxygens. In comes along carbon monoxide, which has a 200 times affinity. It knocks off the oxygen and we have this. Well, think of Le Chatelier. If I give so much oxygen, that is going to increase my products, which shifts everything to the left, which is going to cause offloading of carbon monoxide. That's A. Additionally, carbon monoxide can literally just combine with O2 and that forms CO2 and that gets rid of the carbon monoxide. So yay, we definitely want to give supplemental exogenous oxygen in this case. Methemoglobin. So iron is normally in the 2+ state. For whatever reason, just reactive oxygen species, it just occasionally is oxidized to the 3+ state. Now, when it's oxidized to the 3+ state, that particular heme group is now very low affinity for oxygen. Somehow it has a conformational shift of the whole hemoglobin tertiary structure that the other subunits now have an increased affinity. So I guess the specific effects might depend on the extent of the methemoglobinemia. The blood becomes brownish. That can be diagnostic. And I would also note that the oxidized iron heme group has a slightly higher affinity for cyanide, which will come back into play in a second. So like we said, normally we're in this state, but just normal processes, we have free radicals all over our body due to cellular respiration, will oxidize this into the 3+ state. Nitrates also are going to further oxidize this. Things, our anti-malarial medications also, flavabines will also induce radicals, which can cause this to become more methemoglobinemia. Now, again, everybody who has normal phenotype, they have ways of reducing the iron back to the 2+ state with this enzyme. This guy online, I didn't name him this, but online he's people call him Papa Smurf. He went on a bunch of talk shows. Apparently he has a defect in this. Well, actually, I heard two things. One, I heard he had a bunch of silver, which he thought was a remedy for some illness. I don't know if that's true, but I also heard that he has a genetic defect, which means he cannot go from the 3+ state to the 2+ state, and so he can't bind on to oxygen very well, hence his blue characteristic. So now a treatment for this is methylene blue. Methylene blue is an alternative route to reduce the 3+ back to the 2+ that does not require this. So if you have a bunch of methylene blue, you can make this go back to the normal 2+ state. That's a good therapy. Cyanide poisoning. So apricot, peach, cherry pits have tons of cyanide. There's an almond smell to cyanide. So a little bit of this amygdalin is in almonds as well. Not that much, not a high amount, and nobody should be eating the pits of these fruits anyways. Obviously, people commit suicide, Hail Hydra, with the cyanide pills, and Hitler famously. And so you're also going to have cherry red skin here. Why? Because your body can't use, so we're going to come back to this in a second. Cyanide inhibits, maybe more strongly than carbon monoxide, complex 4. And if complex 4 is inhibited, that means I'm just going to have oxygen levels build up. So my tissue oxygen levels are actually going to be really high, which means when my blood flows through, it doesn't really want to drop off oxygen because the tissue oxygen level is really high, which means we're actually going to have a really high venous concentration, or venous saturation of hemoglobin. So this high venous hemoglobin saturation is going to make this particularly red skin. And again, in postmortem, you're going to have more blood pooling in the venous system, so it's going to be even more pronounced. You have an almond smell. I've heard that not everybody smells this, and it's sometimes just too faint for anyone to detect, but theoretically there should be an almond smell. All right, cyanide treatment. Hydroxycobalamin, this can bind cyanide and you can pee it out more easily. Nitrates, these will oxidize the hemoglobin from the 2+ state to the 3+ state. This is methemoglobinemia. How is that helpful? Well, remember, methemoglobinemia, one weird point of it is that it actually has a higher affinity for cyanide. I guess that kind of makes sense, right? If we're making it from a 2+ to a 3+, it's going to be even more attracted to negative things. So now that it binds, it's not like I want my hemoglobin to be binding to cyanide, but if it's bound to the hemoglobin, it's not causing damage in my cells. So sequestering is sort of the lesser of two evils, and maybe we can slowly excrete it from our body over time. So this is a second treatment. Third treatment is kind of like the first one. Instead of binding, why don't you just convert cyanide to thiocyanate? Then it can be excreted out of the urine more easily. So for all of these, note that there might be slight homeostatic feedbacks, right? Where if your oxygen levels go low or high, you're going to make more erythropoietin, and then you're going to have more erythrophoresis. You might have more or less red blood cells, but at the same time, keep in mind that takes 2 weeks to complete, and most of these hemoglobin poisonings are relatively acute phenomena. So let's start with these three. These should not affect the amount of red blood cells on an acute level. or the amount of hemoglobin that any red blood cell has. So that's going to be normal. Anemia, low red blood cells, or red blood cells aren't making iron or excuse me, hemoglobin or something like that, heme. So it's going to be low. Polycythemia is going to be high. Let's think about hemoglobin saturation. So carbon monoxide, this competes with oxygen. So the amount of specific oxygen saturation is going to be low. But remember that pulse oxes just look at hemoglobin saturation period, not necessarily just oxygen saturation. So this actually might be high. Methemoglobinemia is going to be low. Yes, technically, when I oxidize one of the heme states, that makes the other subunits have a higher affinity. But depending on the level of oxidation, we can imagine if there's so much Fe2 pluses becoming Fe3 pluses, just there's very low affinity for oxygen, and so I'm overall going to have a low saturation level. For the cyanide poisoning, it doesn't. Usually, your arterial values are really just have to do with the lungs and how much air is being ventilated in and how much diffusion is happening. So nothing's going on with your lungs. So the actual arterial hemoglobin saturation is completely fine. The issue is the venous one is going to be high because, as we said, complex 4 is inhibited, so the tissue oxygen levels go up. So there's less incentive for the hemoglobin to then dump off the O2. So it holds on to it. So the venous saturation is up. This attributes to this helps explain the cherry red skin that we might find. And then we're going to pick up less from the lungs, I guess. But because we already had more and we're picking up less, you're going to have a normal arterial amount. So that one's a little tricky. The saturation levels are not affected in these. We just have more red blood cells or less red blood cells. None of these three are going to affect the amount of arterial oxygen, which pretty much hypoxemia just has to do with ventilation and diffusion and how much, how well we can do gas exchange in the lungs. Same thing for these as well. Now the total O2 content is going to be a little bit low in carbon monoxide. Again, one way you can think about it is if either of these is low, it's going to say that you're going to have a low total O2 content. You can't pick up as much because of the carbon monoxide taking the active site in one of the subunits. Same with this is low, so that should be low. Both of these are normal, so this should be normal. I guess in this case, that's going to explain the low status, and that's going to explain the low status. Now, the treatments, supplemental oxygen, we said, can do a Le Chatelier shift to the left, kicking off carbon monoxide, or it can combine with oxygen to make CO2. Methylene blue is an alternative route to reduce the Fe3 plus state to the Fe2 plus state. Hydroxycobalamin binds and can be peed out. Sodium thiosulfate can converted to thiocyanate, which can be is more soluble, can be peed out more easily. Nitrates are going to oxidize Fe2 plus to Fe3 plus. Fe3 plus can bind onto the cyanide, sequestering it so it doesn't damage the cells. What if I have anemia? Well, give somebody erythropoietin and they can make more red blood cells. Or you can just give them a transfusion. What if you have too much blood? Just do a phlebotomy, take some of that out. Remember that carbon monoxide poisoning and cyanide poisoning, these can be confused with one another because they both can produce the cherry red skin, especially the cherry red lips. They can also inhibit the electron transport chain, but we can mainly note the difference here and here versus here and here to differentiate them. Carbon monoxide and methemoglobinemia, both are going to induce left-shifted hemoglobin curves, but again, there are differences between the two graphs and the treatments that you should be able to differentiate them.